Good morning, welcome to new lecture. Today I will review several examples regarding the equilibrium of rigid body and reactions. For example, assume we have simply supported beam. Simply supported beam means one support, it is pin support, another support, it is roller support. The length for this beam, it is L. This beam is subjected to uniform distributed load. The intensity of the load, it is, for example, W pound per feet, and the length, it is L feet. I want to find reactions in this beam, point A, point B. Here at this point we have two reactions, AY, AX. Here I have one reaction, BY. So, because it is in 2D space, it is in plane structure, so I can write three equilibrium equation. Equilibrium of forces in horizontal direction is equal to 0, so summation of force in horizontal direction is equal to 0. AX will be 0. Summation of forces in y direction equal to 0. This means AY plus BY, both of them upward, positive, minus intensity of the load times the length of the load W times L, it will be resultant force equal to 0. Summation of moment respect to one support is equal to 0. For example, summation of moment respect to point A is equal to 0. AX and AY both will pass through A, so will not create any moment respect to point A. BY times the distance, it is L, minus W times the length, it will be W times L, it will be resultant force, times the resultant force up to point A. Resultant force will be in the centroid of this rectangular, so times L over 2 is equal to 0. From here, I can find BY is equal to WL over 2. If I plug here, I will find AY is equal to, again, WL over 2. This is a very simple example. Let's look at the next one. Next one, it is again simply supported beam. Instead of distributed, uniform distributed load, this time assume it is subjected to non-uniform distributed load, and the shape, it is triangle like this, and here it is W pound per feet. I want to find reactions again. Here again, summation of forces equal to 0. From here, AX is equal to 0. Summation of forces in horizontal direction is equal to 0. So AX will be equal to 0. Summation of forces in y direction equal to 0. From here, I can write AY plus BY minus resultant force. Resultant force means the area for this triangle, it will be W times L times 1 over 2 is equal to 0. Another equilibrium equation, again summation of moment, for example, respect to point A is equal to 0. You can write respect to point B or A. I'm writing respect to point A. So BY times distance L, it wants to rotate this beam counterclockwise, so positive minus W times L times 1 over 2, this will be resultant force. Where is the location of resultant force? In the centroid of this triangle. The centroid distance will be 2 over 3 times L from point A times 2 over 3 L is equal to 0. From here you can find Vy will be equal to WL over 3, and if you plug here, from here you can find By is equal to 2W over 2WL over 3, and if you plug that By here, from here you can find from this equation Ay is equal to WL over 3. Let's look at the next example. Next example, assume you have cantilever beam. Cantilever beam means one end is fixed support, another end is free. The length for this cantilever beam, it is L. It is subjected to, for example, distributed non-uniform load. The shape, it is triangle, and this is again W pound per feet. This is L feet. I want to find reactions. If this is point A, this is point B, reaction will be AY, AX, and moment at fixed support MA. So again, it is in plane structure, it is in 2 dimensions, so I can write 3 equilibrium equations. Summation of force in x direction is equal to 0. From here, AX will be equal to 0. Summation of forces in vertical direction equal to 0. From here, I can write AY minus W times L times 1 over 2 is equal to 0. AY, it is upward, positive. W times L times 1 over 2, it will be area for this triangle. The resultant force will be downward, negative, is equal to 0. From here you can find AY. AY will be equal to WL over 2. If I take moment respect to point, for example, B, and put equal to 0, I can write respect to point B is MA, I assume counterclockwise direction, so it is positive MA. It wants to rotate this beam respect to point B counterclockwise, minus AY times L, AY times L. It wants to rotate this beam respect to point B clockwise, so negative, plus moment created by this external load respect to point B, it will be again counterclockwise, so it is positive, positive W times L times 1 over 2. This will be entire resultant force. Where is the location of the resultant force? From this side, from the tip of triangle, it will be 2 over 3 times L times 2 over 3 L is equal to 0. You can put AY from here and find MA. Let's look at the next example. Assume I have simply supported beam. This beam is subjected to concentrated moment at midspan, point A, point B, point C, L over 2, L over 2, and here I apply concentrated moment M at point C. I want to find reactions again. Again, it is in 2 dimensions, it is in plane structure. I can write 3 equilibrium equations. So this will be AX, this will be AY, this will be By. So summation of forces in horizontal direction equal to 0. From here Ax will be equal to 0. Summation of forces in vertical direction is equal to 0. From here Ay plus By is equal to 0, because there is no any force in vertical direction. This is not force, this is moment. Summation of moment respect to point A is equal to 0, because Ax and Ay both passes through point A, will not create any moment respect to point A. By times the distance L, it wants to rotate this beam respect to point A counterclockwise, so positive By times L minus this M, it wants to rotate this beam respect to point A clockwise, so negative M is equal to 0. From here you can find By is equal to M over L. If you plug By here, you can find Ay will be equal to negative M over L. Negative M over L means I assume Ay in wrong direction. Negative means I should change the direction of this reaction. If I show downward, now I can write it is positive M over L. Downward M over L, upward M over L. You see, the force, action force, it wants to rotate this beam respect to center clockwise. Reaction produce couple force, and this couple force will create moment respect to centroid counterclockwise. So they will cancel out each other, and the magnitude will be M over L times L over 2 plus M over L times L over 2. So answer will be equal to M. So for M action, there is a M reaction. It is the magnitude, it is equal, and the direction, it is in opposite direction. So it will cancel out the action, and this beam will remain in equilibrium. Next example, it is one concrete slab in 3 dimensions. Let's look at this example. It is one concrete flat slab X, Y, Z direction. This is concrete slab. It is in XY plane. It is in rectangular shape. Rectangular shape concrete slab, and it is hanging using 3 cables, one at point B, another at point A. So this is TB, this is TA, another at point C here, TC. So I have flat slab in XY plane. It is hanging using 3 cables at point B, A, and C. Dimension, the length for this slab, it is 4 meters. So up to center it will be 2 meters. 2 meters. Point B exactly it is midpoint, so it is in 2 meters. The width of this slab is 2.5 meters. But there is one concentrated load, external load here at this point. This concentrated load magnitude, it is 15,000 Newton. And the coordinate for that point, if I show for example with point O, from here in the X direction, this will be 1 meter, 1 meter. So the distance until the edge, it will be 1 meter. And in the Y direction, this will be 2 meter. This will be 0.5 meter. So point O coordinate. In the x direction it is 3, in the y direction it is 0.5 meter. Here we have one external load, 15,000 Newton downward, and this slab weight is given. The mass it is 2,400 kilogram. So the weight W will be equal to mass 2,400 times gravity 9.81 Newton. This will be the weight. We want to find the tension force in these cables. I want to find TA, TB, TC, tension force in these cables. So, let's first I can write equilibrium of moment respect to y-axis. If I write that, let's see which one is better. The first, no, it is better I write the equilibrium of moment respect to the x-axis. In that case, I can find tension at point C, at this point, TC. If I write summation of moment respect to x-axis and I put equal to 0, I can write TC times the distance 2.5 minus 15,000 times distance up to x-axis 0.5 minus weight 2,400 times 9.81 times the distance from center up to x. It will be half of 2.5, it will be 1.25 meter is equal to 0. TB passes through x, so will not create any moment respect to x. TA will pass through x, will not create any moment respect to x. So this will be equilibrium equation. From here I can find TC. TC will be 14.8 kilonewton. So I converted to the kilonewton. The answer you will divide by 1000. Answer I will you see I show in kilonewton. If you find answer from this equation, it will be in Newton. After dividing by 1000, you can write in kilonewton. Next one, I can write equilibrium of moment respect to the y-axis. In that case, it will be TC times distance 4 plus TB times distance 2 meters minus 15,000 times distance 3 minus weight mass times gravity times distance 2 is equal to 0. You have TC from here, you will plug here. From this equation you can find TB. TB will be equal to 16.5 kilonewton. Now after finding TC and TB, the last one TA, you can find using equilibrium equation of forces in vertical direction in the z direction equal to 0. So you can write TA plus TB plus TC minus 15,000 minus weight 2,400 mass times gravity is equal to 0. You have TC, you can plug here. You have TB, you can plug here. So from this equation you can find tension force in cable at point A. It will be 7.27 kilonewton. Let's look at to the next example. Next example is truss structure. Later on I will explain what is the truss and how we can solve trusses. But for now we want only find reactions, and we can find that. So assume we have this structure. Point A, point B, 2 meter, 2 meter, 2 meter. The height for this truss, it is 2 meter. It is subjected to 3 external forces. One of them it is horizontal, 5 kilonewton. Another here, 6 kilonewton. Another here, 8 kilonewton. I want to find reactions. Here again, this structure is in 2 dimensions, it is in plane structure, so I can write 3 equilibrium equations. Summation of forces in horizontal direction equal to 0. From here I can write AX minus, if I show, for example, AX in this direction, AY in this direction, and BY in this direction, I can write negative AX plus 5 is equal to 0. From here, AX will be equal to 5 kilonewton. Summation of forces in vertical direction equal to 0. So I can write AY plus BY minus 6 minus 8 is equal to 0. Summation of moment respect to point A is equal to 0. From here I can write BY times BY times 6 minus BY times distance 6, it wants to rotate this truss counterclockwise, so positive, minus 6 times 2, it wants to rotate this truss respect to point A clockwise, so negative. 6 times 2 minus 8 times 4, 8 times 4 minus 5 times distance, 5 times height, 2 meter. Again it wants to rotate this truss respect to point A clockwise, so negative 5 times 2 is equal to 0. From here you can find BY. From this equation you will find BY equal to 9 kilonewton. If you plug here you will find AY will be equal to 5 kilonewton. Okay, next example. Next problem, it is one beam. We have pin support here, and it is hanging at point B using one spring. The length for this spring, it is 2 feet. The K for this spring, K, stiffness of spring is equal to 50 pounds per feet. Initially, the length it is 6 feet. This is our structure. Then, we are hanging one mass here, one block at midspan. Weight for this block, it is 200 pounds. In addition, I apply one concentrated moment at point A. The magnitude of this concentrated moment, it is 100 pound-feet. So initially beam was in horizontal direction, it was level. Then after adding this block and that moment, it will rotate respect to point A because we will have elongation at the spring. So it will rotate like this. What is the theta for equilibrium? I want to find theta in order to keep this structure in equilibrium, or after adding this block and this moment, what is the tilt angle at equilibrium point? So after adding this, what will happen? This block will move here, 200 pounds. Now this inclined length will be 6 feet. So the horizontal length now will be 6 cosine theta, entire length. And this elongation will be 6 sine theta. So force inside of a spring, if I show with F is equal to the Kx, stiffness times deformation. Stiffness it is 50, deformation it is 6 sine theta. So this will be force inside of spring. That force will be at point B. So if I cut it and I draw free body diagram, now weight is here. Weight at midspan is 200 pounds, and from this weight to this support location, it is from here to here, it is 3 in the inclined direction. In horizontal direction it will be 3 cosine theta, and this 3 cosine theta is perpendicular to the weight direction. So if I write summation of moment respect to point A equal to 0, I can write F, force inside of a spring, times distance. Which distance? This is inclined distance and it is not perpendicular to the load, that is 6 feet. But this distance, horizontal distance, it is perpendicular to the direction of the force. That will be arm for creating moment. So FB times 6 cosine theta. It wants to rotate this beam respect to point A counterclockwise, so positive, minus this 100, it is external moment I apply, it is in clockwise direction, so negative 100 pound-feet, minus weight 200 times distance, again distance perpendicular to the weight direction, so it is 3 cosine theta, 3 cosine theta. Let's see, F times 6 cosine theta minus 100 minus 200 times 3 cosine theta is equal to 0. Instead of F, you can plug in terms of theta. If I plug this, this will be, that will be 1800. Instead of F, I plug 50 times 6 sine theta, so it will be 1800 sine theta cosine theta minus 100 minus 600 cosine theta is equal to 0. If you find theta angle from here, from this equation, theta will be 85.2 degrees. Okay, I solve one more problem. Assume we have simply supported beam, point A, point B. This beam is subjected to non-uniform distributed load, 6 feet, 6 feet. This is triangle shape until mid-span. It will be 4 kips per feet. I want to find reactions, so this will be AY, AX, BY. Again, it is very simple problem. It is in 2 dimensions, 3 equilibrium equations. So summation of forces in horizontal direction equal to 0. From here, AX will be equal to 0. Summation of forces in vertical direction equal to 0. It will be AY plus BY minus resultant force for this. It will be area underneath of triangle. So it will be 4 times 6 times half is equal to 0. Then you can write summation of moment respect to point A equal to 0. So it will be By times 12 minus resultant force 4 times 6 times half times the distance of resultant force up to point A. It will be 2 over 3 times 6 times 2 over 3 times 6 is equal to 0. From this equation you can find By. By will be 4 kips. If you plug By here, you can find Ay. Okay, I think it is enough for today. Thank you so much for watching this lecture. See you next session. Bye bye.